what is the continuously compounded rate of return? When we talk about interest rate, sometimes we quote interest rate in a simple rate of interest. As a simple interest rate, but sometimes people quote interest rate using the continuously compounded rate of return. So let's go over the idea of the continuously compounded rate of return. Now, let's start with one simple example. So imagine a situation where you borrow $100. So you borrow $100 now, and 1 year later, you have to return $100 principal and also $10 interest. So in this simple example, usually if you ask what is the rate of return, the answer will be simple. Principal is $100, the interest is $10, so the interest rate is 10%. So $100 becomes $100 plus 10, which is 110, so the interest would be interest rate would be 10%. So this is the simplest situation. Let's change the example slightly. Here, instead of paying $10 interest 1 year later, what if you pay interest 2 times and each time you pay $5 interest? So this is, let's call this first situation. And second situation, instead of paying $10 interest 1 year later, you pay $5 interest six months later, and another $5 interest one year later. So in this case, what is the interest rate? It's slightly different from the first situation, because if you think about compounding, then the first $5 interest will also earn extra interest for the second half of the year. So if you consider that, then in the end, you will get more than the $10 interest eventually. So if you apply the idea of compounding, then the correct interest rate in this case would be, so first you apply 1 plus the interest rate of 5% for the first 6 months. And for the second 6 months, again, you get $5 interest. So you will have to apply this one more time. And the interest rate will be obtained from this formula by subtracting 1. And if you calculate this number, it will be 0.1005, which is 10.25. 10.25%. So by considering the effect of compounding, the effective interest rate is a bit higher in the second case than in the first case. Now let's make this example a little bit more complicated. Instead of paying $10 in 2 separate times, as in the second case, let's think about splitting $10 into more intervals. So instead of here, let me write here. So third possibility. So you split $10 into n times, and so you pay interest of $10 n times, and each time you pay $10/n. And you can apply the same logic as in the second case to the third case. Then you can just start from this formula and apply here. Then the first time the interest would be 1 plus 0.1/n. So that's the interest for the first interval. Then for the second interval, you repeat the same thing. And there will be n of this expression, and you subtract 1. And this will be the effective interest rate when you pay $10 by splitting $10 into n pieces and paying $10/n each time. So maybe you can write this like this to make it simpler. Now, starting from here, you can think about the limit of this situation. That is, if n is a very, very large number, what will happen to this number? So the fourth case. So fourth case, you pay $10 interest a lot of times. So n is very large. In that case, this number will converge to some other number, and here you need a bit of algebra, but let's just write this as and if you work on this expression further, you can write this as using the symbol e, the exponential operator, and you can write this as e to the power of 0.1 minus 1. So starting from the first case, you can see that by splitting the same $10 interest into 2 times, n times, and many times, the number will be slightly larger. So this number will be slightly larger than this number. And in this situation, we say the interest rate we can say that the interest rate is exactly this number, or we could say continuously compounded interest rate is 10%. So if you think about this, these terms, continuously compounded, you can gather the meaning of this expression from this example. That is, we are applying the compounding formula many times. In the limit, we are applying this continuously. So in this situation, the interest is paid little bit by bit, continuously. So we call this interest rate here 10%, and of course this 10% is coming from this this number. That is, total interest paid for the during this period is 10%. So we call this continuously compounded interest rate of 10%. Now let's think about this number a little bit more in terms of algebra. So this 10% was read off from this part. So when the interest rate is e to x minus 1, where x is a small number that is close to 0, we may say interest rate is e to x minus 1, or we may say continuously compounded interest rate is x. So we can say either way. To read off x out of here, you can note that if you take the log of this expression, then of course you will get x. So another way to think about continuously compounded interest rate is to say that we are taking logarithm of the regular interest rate plus 1, and that's what we call continuously compounded interest rate. So the question one may ask is, why do we take logarithm of interest rate plus 1 instead of just using the regular interest rate? Or if I write this as R to indicate interest rate, we can write this as 1 plus R. So one may use the regular interest rate R, or you can add 1 to the interest rate and take the logarithm of this number and use the continuously compounded interest rate. But why do we do this? The main reason that we want to take the logarithm of the interest rate is it actually helps in some situation in terms of algebra. If we quote the interest rate as this continuously compounded interest rate or logarithmic interest rate, this will help us in calculating, especially when you think about interest rates of different time periods. Then if you work with the log interest rate, this will make things easier. Let's think about one example why this is why this would help. So I'll write down here again. So R is the interest rate. And log of 1 plus R so I'll call it X. Consider this example. Let's say the interest rate in the first year is 10%, and the interest rate in the second year is, say, 20%. And if the question is, what is the total interest rate for this 2-year period total? One thing that should be obvious at this point is that you cannot just add these two numbers and say the total interest rate is 30%. This is not the correct way to calculate this number. You need to consider compounding. Then the total interest rate would be, of course, 1 plus 10%. So that is 0.1. That's for the first year. And for the second year, it's 1 plus 0.2. To express this as interest rate, again, you will want to subtract 1. So that's the total interest rate for the 2-year, for this 2-year period. Well, this is okay, but it's not very simple to work with, especially if you have multiple years, not just first year, second year. If you have 10 different years, the formula will become rather messy. Now, for the same situation, let's say we express the interest rate using the continuously compounded interest rate. Then for the first year, instead of saying it is 10%, you will take log. So you will say the interest rate is log of 1.1. And for the second year, you will say the interest rate is log of 1.2. And again, to answer the question, what is the total interest rate? Then you will look at here, add 1, so this part will disappear, and take log of the whole expression. So you will get log of 1.1 plus log of 1.2. So if you look at this part, then interestingly, we can express the total interest rate as the interest rate of the first period plus the interest rate of the second period. So we can just add the interest rates of different periods, and we can obtain the total interest rate. So this is this example shows that if you work with the continuously compounded interest rate, adding interest rate becomes easier. Instead of multiplying like this, you can just simply add continuously compounded interest rates over different periods. And that's that makes life easier, and that's why people prefer continuously compounded interest rate. Now, the one thing you have to be careful when you work with the continuously compounded interest rate is as you can see in this example, the situation is identical. When you work with the regular interest rate or with the continuously compounded interest rate, nothing changes. The underlying situation is identical. It's just quote convention. That is, it's a matter of how you quote interest rate. It's not about the underlying situation. The underlying situation is identical. You just decide to quote interest rate, in this case using the simple interest rate, and in the other case you decide to quote interest rate using the continuously compounded interest rate. Just to clear up possible confusion, Now, when I introduce the concept of the continuously compounded interest rate, I talked about the situation where the interest is paid continuously little bit by little bit over during the certain period. That's just, we talked about that as a way to motivate this idea, but it doesn't really matter in the end whether interest is paid once or multiple times. You can always quote the interest rate using the conventional interest rate or the continuously compounded interest rate, regardless of the number of times interest is paid. So another way to say the same thing is, given certain situation, you can calculate the regular interest rate after applying all the compounding. Once you get the regular interest rate, you can convert the interest rate into continuously compounded interest rate using this formula. And therefore, it doesn't really matter in this case whether the $10 interest was paid once, and that's why we have 10% interest, or perhaps the interest was paid 2 times, a bit less than $5, and we applied the compounding and we got 10%. So it doesn't really matter how the interest rate is, how the interest is paid. So these two should be separated. The description of how interest is paid is independent from how you decide to quote interest. This is your decision, and this should be given by the situation. So do not mix these two. Once you clear up that part, then the use of the continuously compounded interest rate would not be too complicated. Okay.